Good morning, good afternoon, good evening. I'm really sorry about this problem. It's always different solutions and different problems. Sorry about it, but I will catch it up anyway, so I will not keep you longer here. I will just speak faster to make sure that you will make to your next appointment. Sorry about the trouble. So everybody is talking about big data, and I was thinking I will give you kind of introduction to the big data world. What is it all about, and why should we care about it? Very briefly about myself. So I have graduated from University of Helsinki. I hold a master's degree on computer science, and currently I'm working on my doctoral studies. I also work as a researcher and lecturer at the computer science department. I research and lecture about databases, big data, multimodal databases, and methods and tools for utilizing semi-structured data for decision making. Very interesting areas, all of them, and somehow related to each other. I've been working with Oracle products since 1993 and on IT since 1990. Anything to do with data and databases, I simply love it, and that's me. I'm the CEO for Miracle Finland, which is a small consulting company in Finland. I'm an Oracle ACE director, ambassador for EMEA Oracle Users Group community, public speaker, and author. I won the Devi for Database Design category 2015, and I have written 2 books. The first one about database designing, and the second one with 4 other Oracle ACE directors, Arup Nanda, Brendan Tierney, Martin Woodlake, and Alex Nuyten. It's about SQL and PL SQL. Very interesting book, I think. And now to the topic. So what is big data? The first thing here is that the name big data is really confusing because it applies that there is a size in data which categorizes it to big data and small data and maybe semi-sized data. But no, that's not true. There is no size that makes the data to be big data. It only depends on the capabilities. So the data is big when traditional processing with traditional tools is not possible due to the amount or the complexity of the data. So it's not about the size, it's about the processing of that data. So for instance, you cannot open an attachment in an email, or you cannot edit a photo. Simple examples. In big data, we always talk about 3 V's. First of all, volume, the size or the scale of the data. Velocity, which is the speed of change. We are doing analyses on streaming data. And thirdly, variety, which means different formats of data sources and different forms of data. The data can be structured, semi-structured, or unstructured. In the relational database world, we have the schema first. We design the database and the schema, and after we've done that, we start inserting data. But in the flexible schema data, FSD, we have the data coming in to our database without any schema. And the schema might be created later or maybe never, depending if we are using that data or not. So volume and velocity are kind of familiar to us already. We've been working with data for ages. And they are easy to understand, and we have plenty of technical solutions to solve these problems. But variety leads to diversity and complexity. So having these different kind of data in our system, in combination with all the huge amounts of data, we might end up having some difficulties. Users cannot query all their data in once in just one single high-level declarative query language. Instead, they have to use different query languages for querying different kind of data, and they need to implement their own joining algorithms to join between relational data and this FSD data. Joining is not only a technical problem, it is also a logical problem. You just had this FSD data coming in without understanding what you have. So how did you know how to join that data with your relational data? What columns or whatever attributes or data to use for joining? So without understanding your data, it is very difficult to join. So this problem with different query languages and joining, it is a severe problem for our systems. But also many specialized systems lack essential advanced functionalities, such as ACID and fine-grained security, that are the norm in relational database management systems. So relational database management systems are supporting semi-structured and unstructured data. I can't say they are not. So all leading relational database management system platforms have support for XML data, for the management, and also for querying and managing relational and XML data together. And many relational database management systems, including Oracle, have support for JSON data management. JSON and relational data can be queried together in a relational database management system. And especially in Oracle 12.2, there's a lot of interesting things that makes this very easy. We also have lobs for characters and for binary to hold unstructured data. So we do have solutions for this already in the relational database management systems. So a relational database management systems can be extended to handle FSD by following these three principles: leveraging document store model, opening SQL with extension functions to declaratively query and update FSD, and adopting relational indexing and inverted indexing strategies. So these principles can be implemented in the RDBMS kernel at data storage, query, and indexing layer to make relational database management system a unified platform to manage both kinds of data. The underlying philosophy for the principles is simple. Treat schema as if it were data. Store, index, and query schema along with the data for FSD. But now, we just solved the problem with different kind of data, but now the volume and the velocity hits. Is the relational database management system able to handle the volume and velocity when we have this kind of different kind of data? And not all the data is equally valuable, equally reliable, etc. Disk is expensive in our Exadata box. Do we really want to save everything there? Even the cat videos and the cake recipes? That brings other V's. Veracity means the uncertainty of the data. The data is worthless or harmful if it's not accurate. And it can actually be harmful on purpose, like viruses. Viability, validate that hypothesis before taking further action. And in the process of determining the viability of a variable, we can expand our view to determine other variables. The value, the potential value of the data. Variability refers to data whose meaning is constantly changing, inconsistency of data. For example, words and contexts. So the same word in different contexts might mean something completely different. And visualization is the way of presenting the data in a manner that's readable and accessible. Especially for our end users, visualization is very important. But I would say it's also for me because picture tells so much more than just words. So finding the best architecture for your purpose might need a little bit thinking. So if a salesperson comes to you and gives you one solution, it might work or it might not work. You need to really know what you are trying to do. There are plenty of research going on the area, which definitely means that the solutions we have at the moment are not the final solutions. This is an area that is evolving all the time, and the solutions are getting better and better all the time to meet our needs. I wanted to add something from Gartner. They made a research, critical capabilities for operational database management systems in December 2015. And the things they found, the key findings are operational database management system use cases have expanded beyond traditional transactions. That's exactly what we spoke earlier, that we cannot use the same procedures to handle our data as we used to do. It's not just enough. Relational operational database management system products and emerging NoSQL and multimodal offerings are entering the market to address some of these new use cases, creating opportunities for best fit engineering, but threatening established company standards for information management, which means that there's a lot of going on in the area. Changes are coming. Incumbent vendors are responding by expanding the capabilities of their relational database management systems into multimodal territory, but hedging their bets by also adding specialized products to their portfolios, creating both multimodal and multi-product choices and confusion in the mind of buyers. So instead of having one solution, you will have at least two solutions from each vendor because they are not sure which one will win, multimodal or multi-product. And they will offer you several solutions, and that is causing confusion. What do Gartner recommend? Their recommendations are: identify the use cases you have under consideration and assess your current operational database management products' fit, costs, deployment options, and skills requirements. So make sure you know what your requirements are. What do you want to achieve? What do you want to do? What are the requirements? Evaluate potential alternative product selections based on best fit engineering that maps to your use cases, and do not pay for features you don't and will not need. So when the salesperson comes to you and offers a product which has plenty of wonderful features which you don't need, it's possibly not the product you need. And being able to understand this, you need your requirements. Issue RFP and conduct proof of concepts. Especially when we are doing something completely new, like the big data world is completely new, we need to understand what we are doing. So with a POC, you get a lot of new knowledge. You have your requirements, you have selected some potential tools, and you make a POC with them. First of all, you learn about the tools, but secondly, you will learn about your own requirements that might not be complete yet because you didn't know what you want. The problem here is that since it's a new world, our imagination is a limitation here. So we can't even imagine what we want to do in the new world. So having some insight in some products brings us that knowledge. Update your standards, training, and support organizations to manage, qualify, and accommodate additional requirements if your technology portfolio is expanding. Most likely, your technology portfolio will be expanding. Most likely, you will need new knowledge, new technology skills, new standards. So this is really an important point. So what do Gartner see in the future? Strategic planning assumptions. By 2017, all leading operational database management systems will offer multiple data models, relational and NoSQL, in a single database management platform. And as I mentioned earlier, that's already happening. So most of the operational database management systems offer both relational and NoSQL features in a single database management platform. Through 2018, 50% of small operational database management vendors will disappear due to acquisitions, merges, or business failures, which might be true. 50% is a big number, but we will see what happens. And by 2017, the NoSQL label will cease to distinguish database management systems, reducing its value and resulting in a label falling out of use. This means that by the end of this year, nobody will use the term NoSQL anymore, which personally I like a lot, because I think, as I mentioned earlier, big data is a bad name, but also NoSQL is a very bad name for the use case it's used. So I won't be sorry if we don't use this term anymore. Of course, those solutions still remain, but just the name would disappear. So what is big data for? The idea of big data is not to save as much data as possible and never use it. So that's definitely what big data is not. So all the data you can find, save it, and never use it because you don't understand what you have. That would be the worst misusing of big data. Big data is for data exploration. Data exploration is to efficiently extract knowledge from the data, even though you do not know what you are looking for. That is what's called data exploration. It's not a new thing. 1977, J.W. Turkey said in his Exploratory Data Analysis book, with exploratory data analysis, the researcher explores the data in many possible ways, including the use of graphical tools like box plots or histograms, gaining knowledge from the way data are displayed. So this is something we wanted to do for a long, long time already. But there are those challenges we already spoke about. There's more and more data, the volume. There's different data models and different data formats, the variety. The loading is still in progress while data exploration is going on, the velocity. Not all data is reliable, veracity. We do not know what we are looking for, value, viability, variability, etc. Most support also non-technical users like journalists, investors, politicians, and we need visualizations. And the worst thing is that all this must be done efficiently and fast. So that brings a lot of challenges and pressure to the technology for big data. Exploratory computing is a conversation between a user and a computer. And the idea here is that the system provides active support to this user and to this conversation. The exploration process is investigation, exploration seeking, comparison making, and learning. Wide range of different techniques is needed. I'm sure you already imagined that. We need statistics, data analysis, query suggestion, advanced visualization tools, and so on. Here's an example, an Acme Band example. Acme Band is a fitness tracker. a wrist-worn smart band that continuously records users' steps and also can be used to track sleep at night. I'm sure you all know this kind of tools. This is the data model for this Acme band. We have Acme user who has location, activities, and sleep. This is not from the original paper. I draw this because I wanted to understand how it works. An example conversation might be something like this. The computer says, it might be interesting to explore the types of activities. In fact, running is the most frequent activity, over 50%, cycling the least frequent one, less than 20%. Second possibility, it might be interesting to explore the sex of users with running activities. In fact, more than 60% of the runners are male. Or the first suggestion, it might be interesting to explore differences in the distribution of the length of the running activities between male and female. In fact, male users generally have longer running activities. The user is interested about the suggestion number 1. It might be interesting to explore the types of activities. In fact, running is the most frequent activity, over 50%, cycling, the least frequent one, less than 20%. Here's the notation that we use for telling that type is running for activity. The user likes this and picks running. Now the computer suggests something more. It might be interesting to explore the region of users with running activities. In fact, while users are evenly distributed across regions, 65% of users with running activities are in the West and only 15% in the South. User likes this and picks South. So we have running in South, and it's related to location, Acme user, and activity. Okay, now the computer suggests it might be interesting to explore the sex of users with running activities in the South region. In fact, while sex values are usually evenly distributed among users, only 10% of users with running activities in the South are women. This is interesting. The user likes it and selects that. So this can go on for a long time because the computer always finds something interesting and the user decides if that's really is interesting or not. So the computer can find a lot of correlations between the data, a lot of patterns, a lot of whatever from the data, but it's user's responsibility to say if that is really interesting or not. Now the user is exploring the set of tuples corresponding to female runners in the South. This user may now ask the system for further advice, just like we did earlier, browse the actual database records that are the result set of this last query, or use an external data source to look for relevant features. And what the user wants to do now is use an external source. The user is interested in studying the quality of sleep and downloads an Excel sheet from a website stating that over 60% of the users complain about the quality of their sleep. So we are now combining two different kinds of data sources. We import this data into our system. Now the system suggests that unexpectedly 85% of sleep periods of Southern women that run are of good quality. And the user has learned something new from the data from two different sources. That is what data exploration is all about. Finding new knowledge from different kinds of data, using both computer and a human. This couldn't be done without algorithms. That is a very big thing in artificial intelligence, in machine learning, in everything in big data world. To be able to perform this conversation, we need many techniques and solutions in different layers, built by differently skilled people. So in the big data area, and especially in data exploration, we need different skill sets. So if you feel that something is definitely not your thing, maybe something else is yours. And all the knowledge you have so far when you've been working with data, databases, and data applications is definitely worth, because all the knowledge is still needed, but added with something else. But first of all, we need these algorithms. Some of them you already have, and some of them must be built. So we need people who are capable of building algorithms and people who are capable of using them. Let's see a couple of examples. What are these algorithms? One of these techniques we just used is called a faceted search. Some people call it faceted navigation, some call it faceted browsing. In Wikipedia, they say it's a technique for accessing information organized according to a faceted classification system, allowing users to explore a collection of information by applying multiple filters. In this example we just went through, activity is a facet and running is a constraint or a facet value. The user can browse the set, making use of the facets and their values, and then inspect the set of items that satisfy the selection criteria. So that is a faceted search. We also need fast statistical operators to compute statistical properties of the data and the ability to compare those properties. For example, subgroup discovery, to discover the maximal subgroups of a set of objects that are satisfying statistically most interesting with respect to a property of interest. We need a statistical algorithm to measure the difference between two tuple sets with a common target feature in order to compute the relative relevance. So we need different kind of algorithms. Let's see a simple example. The difference between two tuple sets. It has 4 steps, and all this done iteratively. It has sampling, comparison, iteration, and query ranking. Let's see how it works. First of all, the sampling. Sample tuple sets to extract subsets and cardinality much lower than the one of the other one. This can be done with different sampling strategies: sequential, random, or the hybrid of those two. So already this one can be done in many ways. And that is the thing with algorithms. We usually have several algorithms to solve the same problem and need to find the one that suits the best here. Then the next step is comparison. The comparison step aims at assessing the discrepancy between X1 and X2 through theoretically grounded statistical hypothesis test of the form test I, X1, X2. So this comparison can be done in several ways as well. It can be numerical or categorical data, by the way. And then the iteration. Repeat the extraction and comparison steps m times, and the jth iteration, a new pair of subset are extracted and tested. The test is computed. If the test rejects the null hypothesis, we stop the incremental procedure since we have enough statistical confidence that there is a difference in the data distribution of TQ1 and TQ2. Otherwise, the procedure proceeds to the next iteration. When we're done with that, we need to do the query ranking. The difference between empirical distributions of the pairs chosen in computed using the Hellinger distance. I have the Hellinger distance here, and if you're interested what it means. So based on this, we can rank the tuple sets to find out those exhibiting the largest difference. So this was a very simple task, but as you can see, it takes a lot of steps and a lot of work to really do it correctly. And that is one challenge in our big data world, to do things correctly, because we have so many different possibilities, so many different algorithms, so many different tools, and so many different whatever. So doing it correctly, in my case, is a big challenge. But there's also different layers. We need techniques and solutions for all these levels or layers of the system. Algorithm is just one part of it and can be used in many layers. But the different layers we have is the user interaction or the user interface, the middleware, and the database layer or the database engine. The challenge for the user interaction is challenges are that the user interface should help the user to find information he or she was not aware of and to find even more information based on the information already found. So it's not an easy task to do. The data is in different formats, large amount of different kinds of data, and analyzing it takes time. This conversation must be fluently responsive. People won't wait for long for the computer to answer. And not all users are IT professionals. The idea here is that they should be able to use this system without being IT professionals, without being able to code or program. The query result visualization to understand the data and to communicate with the exploration software would be very valuable for these people. In the user interaction, in the exploration interfaces, we need systems that assist the SQL query formulation, systems that automate the data exploration process by identifying and presenting relevant data items. We also need novel query interfaces such as keyword search queries over database and gestural queries. This is, by the way, a research area at the moment. A lot of research going on that area. And we need the visualization. Query visualization, the role of visualization for data analytics is huge because the picture tells more than 1,000 words. Visualization tools that assist users in navigating the underlying data structures, tools that incorporate new types of interactions such as collaborative annotations and searches, query result reduction, aggregation, sampling, and/or filtering operations, and query result visualizations. So there's a lot of different kind of visualizations that would help our users and us as well. Not just the result visualization, but also other visualization. And also for the user interaction, user involvement is an important part. There is the relevance of an answer for a specific user. For another user, one answer is very relevant, while to the other one it's not relevant at all. So it should predict users' interest and anticipations in order to issue the most relevant answer. There are some possible techniques like grouping the users in subgroups, classify different notions of relevance, and devise strategies to customize the system response to the user behavior. But still not a simple task. And again, the responsiveness. The conversation must be fluent. Users will not tolerate long computing times, which will bring a lot of pressure to the other layers like middleware. Middleware is building various optimizations on top of the database layer or the database engine. This can be used to improve the efficiency of the data exploration without changing the underlying architecture. The exploration tasks are computationally heavy and can be speed up maybe in the middleware layer with data prefetching and background execution or query approximation. But since there is no silver bullet for anything, we'll see a little bit more about these two possibilities. There's also other possibilities, but these are just some examples. So caching data sets which are likely to be used. First of all, how do we know what will likely be used and what will not be likely used? That is one problem here already. Algorithms again. The trade-off between introducing new results and reusing cached ones. And the main challenge is really identifying the data sets with the highest utility. So how do we predict what to show, what will be asked most frequently, and what will be asked in the first place, because most of the data will probably not even be queried. So It's not easy to build data prefetching that is perfect. Another possibility is query approximation. So the system, instead of giving the accurate answers, will give approximate answers. So it allows users to get a quick sense of whether a particular query reveals anything interesting about the data. But it needs a solution that processes queries on sample datasets, not the whole data, but samples, so that we can have fast query response times. Of course, the problem here is, again, how the samples will be built. How do you know the sample is good enough for our whole data if the data is flowing in all the time and we don't actually know what kind of data is coming in? So building the sample sets is not an easy task. And again, the trade-off here is between result accuracy and query performance. So we get fast response with approximate answers. By the way, in Oracle 12c, we have the approximate functions that can be used for this. And now to the database. So database is all about saving and retrieving data. The way the data is stored defines the best possible ways of accessing it, and the way data is accessed defines the best way to store it. That's something we have learned with relational databases, and it's still a fact. But we might not know what data we will be loading, so we don't know what's coming in. We are just loading it. Remember, we don't have the schema, and we do not know what we are looking for. Remember, the user is trying to find something she doesn't know about. So therefore, we are unable to define the best way of storing the data. So what do we do now? How can the architecture of database systems be redesigned to aid these data exploration tasks? Big challenges. Some examples or some solutions are adaptive indexing, adaptive loading, adaptive storage, flexible architecture, and architectures tailored for approximation processing. What is adaptive indexing? It's creating indexes incrementally and adaptively during query processing, based on the columns, tables, and value ranges that queries request. Indexes are built gradually. As more queries arrive, indexes are continuously fine-tuned. That's what is an adaptive indexing. Adaptive loading. Not all data is needed. Users might want to leave some parts of the data unloaded. And not all data is available. Users might start querying a database system before all data is loaded, and they will definitely do that because data is constantly flowing in. So they are doing the analysis during the loading. So not all data is needed and not all data is available. We also need adaptive storages because there is no one perfect solution for storage layout for all this data. Adaptive storage can be used for different needs of storage layouts. Examples: Octopus DB, a central lock and storage views. H2O supports multiple storage layouts and data access patterns, decides during query processing which design is best for classes of queries. And of course, in Oracle, we have the in-memory columnar stores. I think what we need here is the multimodal database, which is one of the research areas at the moment. It might be a solution, depending how it ends up. But anyway, we need a flexible architecture. So we can tune the architecture to the task at hand by having a declarative interface for the physical data layouts, by having a declarative interface for the whole engine, and using organic databases to continuously match incoming data and queries. We start with a schema that is good enough and schema evolution while the loading and querying. Or maybe the multimodal database. There's also technology that might help, like CPUs versus GPUs, fast implementation of statistical computations over GPUs, graphical processing units. Dividing the workloads to CPU and GPU have been given promising results. So here's briefly what it's all about. A simple way to understand the difference between a CPU and GPU is to compare how they process tasks. A CPU consists of a few cores optimized for sequential serial processing, while a GPU has a massively parallel architecture consisting of thousands of smaller, more efficient cores designed for handling multiple tasks simultaneously. We also need architectures that are tailored for approximation processing, where storage and access patterns are tailored to efficiently support sampling-based query processing. Efficient access and updates of sampled datasets in the database core. For example, Oracle 12 sees adaptive dynamic sampling for the optimizer, or DICE, faceted exploration of data cubes, which combines sampling with speculative execution in the same engine. So design new engines is one of the open challenges and definitely worth it. There are also techniques for large data size like summarizing. Fully pre-computing is not possible in a big data world. You remember the data is just coming and going, and you are not able to pre-compute. And of course, it's not even smart. So the size of data summarized must be large enough to estimate statistical parameters and distributions, but manageable from the computation viewpoint. We also have the data mining techniques. We have histograms presenting on histogram algebra for efficiently executing queries on the histograms instead of the data and estimating the quality of the approximate answers. We need effective pruning techniques because not all node paths are interesting from the user viewpoint, and the ones that fail to satisfy this requirement should be discarded as soon as possible. So just to go to the conclusions. We talked about several V's. I'm sure we can find even more V's. There's volume, velocity, variety, veracity, viability, value, variability, visualization, and so on. Data exploration is about finding new information and knowledge from the data without knowing what we are looking for. There are lots of problems related to data exploration. Non-technical people must be able to use it. High demand on the user interface. We don't know what we are looking for from the data. We need good exploration techniques that must improve on every search. The data is large in various formats and data models. Searching that kind of heterogeneous data fast and efficiently is not easy. And that gives challenges to all the levels: user interface, middleware, and the database layer. I added here 3 A's for the solutions: algorithms, approximation, adaptivity, and 1 F, the flexibility. And these are the keywords for the solutions to my mind. I mentioned you that I've been using some articles in this presentation, and I really encourage you to read these. These are very interesting and will give you more detailed information about what we just spoke about. By the way, the last one is made by Oracle people, and it's a very good paper, number 3. Thank you so much for listening, and I really apologize for the late beginning with the technical problems.